The first intermolecular interaction we're going to talk about is dipole-dipole interactions. Intermolecular interactions are going to be those interactions between molecules, and these interactions are important because they're attractive forces that hold molecules to one another, and they can determine the physical properties of a compound. So, for example, it will keep a liquid in that liquid form or keep solids in that solid form. They affect bulk properties like melting point, boiling point, and solubility. And so we're going to see intermolecular interactions a lot in a lot of lab techniques. We're going to have to understand intermolecular interactions to understand, why does this organic molecule go in and dissolve better in this solvent than this one? And a lot of our techniques are kind of based on that. And so the first type of intermolecular interaction we're going to see is dipole-dipole interactions, and these ones involve those polar covalent bonds we talked about in the previous video. Those polar covalent bonds, those are basically dipoles because we saw that we had one atom in that bond that was more electronegative than the other, so we could draw a dipole. And basically, what's going to happen with these those are going to help the molecules stick together better because they're going to align so that their net dipoles attract each other. So if we think about the dipole in this molecule, we have the chlorine pulling the electron density towards it. If we're thinking about how could this one molecule interact with another molecule of itself, we would have the chlorine from another molecule interacting with the carbon that's delta plus. So that was another way we could show this, the delta plus, delta minus. And what we tend to see is that these dipoles are going to line up so that the delta plus of the one molecule is aligned with the delta minus of the other molecule's dipole. We can also, if we want to draw in the dipole, we can do that as well for both of these molecules. So this is just one example of an interaction. We're going to have multiple types of these interactions, and what's happening and why this is important is that that's helping those to stick together. So these interactions can help the boiling point be higher than compared to if we didn't have this type of interaction, because these molecules are sticking together better, basically. And we say that when the dipoles increase, the molecules become more polar. So that means they're going to be sticking together better. That means they're going to have a higher melting point or boiling point. It also means that they're going to be able to dissolve in polar solvent. So this is where that like dissolves like comes from. If we have a solvent molecule that can also have these dipoles and align their dipoles with that molecule we saw in the previous slide, then we're going to be able to help to kind of draw those molecules away from each other and start to dissolve those molecules in that solvent. And so it comes into play with solubility as well. Just as an example of a question for this section, what compound do you expect to have a higher boiling point and why? So we're thinking about for which one of these two are the molecules going to stick together better, basically, and be harder to separate, take more energy to separate them and make a gas. And so let's draw out the structures of them just so we can kind of see what we're dealing with. So we have our CH3Cl, and we have our CH2Cl2, or our dichloromethane, which is a solvent that you use a lot actually in the lab. So out of these two, which one do we think is going to have the higher boiling point? Well, we're going to go and we're going to look, do we have an atom that's more electronegative than another one? And we definitely do. We have a dipole we can draw here. Alternatively, we could put delta plus on the carbon, delta minus on the chlorine. We actually have two polar covalent bonds in this molecule. We have the one to the chlorine on the left that we've drawn and the one to the chlorine on the right, and that's because we have two chlorines attached now to that carbon. So we can draw both of these. And remember that this carbon is, since it's sp3 hybridized, it is going to be tetrahedral. So basically these dipoles are going to be on one side of the tetrahedron, no matter how you draw this or really look at this, they're going to be on the same side. And so what's going to happen is that that's going to be a stronger effect because now other molecules can align their dipoles with these. And since you're having both of these pulling away from this carbon, you have a really big delta plus here, and you're getting some really big delta minus on the two chlorines, and so you're going to be able to stick your molecules together better for this one here. And so we would expect that the dichloromethane is going to have the higher boiling point than just the CH3Cl, and that's because we have more interactions, more dipole-dipole interactions. And that's going to mean that the molecules can stick together better, so they can stick to one another easier and better because of the dipoles that we have, and so that's going to make them harder to separate, and so that's going to mean that we're going to have a higher boiling point for this particular compound over here.